All right, so now we can talk a little bit deeper about what happens when we impose this octahedral ligand set after thinking about theoretically what happens, this increase in energy when we have a spherical environment or a ligand sphere. And so in order to continue our discussion here, we have to talk about the symmetry of orbitals. And so the different orbitals, just like anything else, when you're talking about the point group of a molecule, has symmetry. They have different symmetries. So as orbitals, they're sphere-like, right? So they're always going to be totally symmetric. So that means if you look at the character table, they're going to have whatever the symmetry of whatever representation has ones all across the board, has ones in every component of that irreducible representation. So usually that's going to be called A1 or A1G. Those are the Mulliken symbols that are usually used. Okay, but S orbitals are totally symmetric. The P, D, and F orbitals have the same symmetry as their functions in whatever character table you're dealing with. All right, so pretend you have some molecule in the C4V point group, and you want to know what the symmetries are of the orbitals on the metal ion, okay, or just in general. And so your s orbital is going to be A1. It's always the one with ones across the board, the totally symmetric representation. Your px, py, and pz orbitals are going to have whatever the symmetry is of those functions. So for px, well, you're going to look for the x function. Now here, x and y turn out to transform together as this two-dimensional representation called E. And so that means the px and py representations actually go together. They transform together. Whenever you do something to the x orbital, it's also going to do something to the y orbital. It's another way of thinking about it. So both the px and py have the symmetry of E in the C4b point group. Pz orbital, well, we look at the z function, that has a symmetry of A1, happens to have the same symmetry as the s orbital in this case. That won't always be true. It's wherever this z function is on the periodic table, on the character table, excuse me. For the d orbitals, well, these are quadratic functions, right, that describe the d orbitals. So we're again just looking for the quadratic functions. Xy, dxy orbital is going to have symmetry where there's xy function of B2. Xz, well, there's the xz. Oh, and look, it transforms together with yz. So both xz and yz orbitals are going to move together, transform together as the symmetry element E. X squared minus y squared, we can look for that. And where is it here? There it is. Sorry, right here, x squared minus y squared, quadratic functions, B1, okay? And then dz squared, depending on your character table, it might be listed as z squared, here it is, A1, or it could be listed as 2z squared minus x squared minus y squared, which remember is the longhand version of what the dz squared orbital function actually is. But here it's using the shorthand nomenclature z squared. And so you can see it also has a symmetry of A1. Some character tables also will show you the cubic functions. By the way, there's ways of deriving where these functions are, what the symmetries are, but we just don't have time to go over that in this course, so we're just going to look it up on the character tables. But you know, these cubic functions correspond to the f orbitals. So if you were curious what the f orbitals looked like or what their symmetries were, here they are. If you were curious about g orbitals, you would have to use what? You'd have to use functions with a polynomial 4, right? So anyway, that's a really key kind of tool that we need to move forward. And now that we know that, what we're going to do, we are talking about the octahedral ligand set. Okay, so what happens to this energy of these 5d orbitals when we go to an octahedral ligand set? We're going to impose OH geometry. So we're looking at the OH character table right here. And what we're curious about is what are the symmetries of the 5d orbitals? Here you can see the z squared orbital is written out as 2z squared minus x squared minus y squared. Remember, that's just shorthand for z squared. So dz squared is going to be have EG symmetry in OH, okay? And it's going to transform together with the dx squared minus y squared orbital. So both dx squared minus y squared and the 2z squared are going to transform together in octahedral symmetry as EG symmetry. The other three orbitals, dxz, dyz, and dxy, are triply degenerate. That means that they have the same energy, and all three of them transform together. See, this T2G representation is three-dimensional. So three things must transform together if they have T2G symmetry. And in this case, it's these xz, yz, and xy functions. So, summary, we're going to have three orbitals with T2G symmetry and two orbitals with EG symmetry when we're in an OH ligand environment. And so that tells you you're going to have two orbitals, two of the EGs, the two EGs of some energy. They're going to have the same energy. And three of the T2Gs are going to have the same energy. Now, how did we know to put these EGs higher in energy than the T2Gs? Why didn't we have it flipped? This is kind of where crystal theory helps us. What we're going to think about, remember, is crystal theory is all about electrostatics. It's all about point charges. So we're going to think about where is the most interaction. And we said that this sort of interaction was repulsive. It's electron-electron repulsion. So if you look at the position of the ligands right here in blue compared to the atomic wave function in orange, you can see that like these lobes of the dz squared are pointed directly on these axial ligands. And look at the dx squared minus y squared. Remember, that's the one that's rotated 45 degrees. You have the lobes directly on the axes. So these lobes of the dx squared minus y squared orbital are directly pointing at these four equatorial ligands. That's a lot of interaction. That tells you that these are going to be relatively high in energy, these EGs. But from the character table, we know that the dz squared and the dx squared minus y squared are degenerate. So we know that they're the same in energy, whatever the energy is. Look at the other three, the T2Gs. These are the XY, the YZ, and the XZ. Look at how the lobes are oriented. They're going through kind of at a 45-degree angle, right through where the axes are. They're not on axis. And because the ligands are on axis, that means the lobes aren't pointed directly at anything. The orange and blue aren't overlapping much. And if they're not overlapping much, that means it's relatively stable, right? Because we're only thinking about electron-electron repulsion in crystal field theory. So that's why the three T2Gs are lower in energy. We call the difference between the EG and the T2G in octahedral symmetry delta O. So O stands for octahedral, delta just means change, right? So it's change in energy, we call it delta O. So our kind of finished crystal field theory diagram when going to an octahedral ligand set looks like this. We start with a metal ion, 5 degenerate d orbitals. We put on a spherical ligand sphere that increased electron-electron repulsion between the ligands, valence electrons on the ligands, and the valence electrons on the atom that caused all of the 5d orbitals to increase in energy. But because we're in a spherical ligand sphere, the energy of all 5d orbitals is the same. Only when we impose octahedral symmetry, OH, do we split the energy into three T2Gs and two EGs. And so you can think about this as the EGs being raised 0.6 times delta O, okay? Or what is that, 3/5, going 3/5 up delta O, whatever this gap is. And the three T2Gs going down 2/5 or negative 0.4 times delta O. Because if you add that up together, right, you have two orbitals that went up 0.6 times delta O plus three orbitals that went down minus 0.4 times delta O. That gets you 1.2 delta O minus 1.2 delta O equals 0. So your center line here didn't change. And that's sort of a very useful concept that we'll see throughout the rest of the course, is that the barycenter, so-called, the kind of center energy line, will always remain the same whenever you do some sort of splitting in energy. So the average energy of the d orbitals remain the same because all we did, right, we didn't really change anything here except for the symmetry. Whenever you have some change in orbital energy just because of symmetry and nothing bigger than that, then you're always going to have this average energy staying the same. It's a very useful principle. dq is another unit that's often used, and people talk about 10 dq. 10 dq is just equal to delta O. It's just calling it something different. I guess people like this 10 dq unit because then you can talk about these going up 6 dq and these going down 4 dq. And so you have 2 times 6 dq because you have 2 EGs plus 3 times negative 4 dqs because you have 3 T2Gs going down in energy equals 0. Okay, 12 dq plus plus negative 12 dq equals 0.